Cambridge IGCSE Chemistry, Paper 2 preparation, tip number 10. So Paper 2 often asks questions combining the ideas on electron properties, the electron configurations of atoms, what the position in the periodic table reveals about the electron configuration of the atoms involved, and the electron configuration of ions. These are generally combined in questions 4 or 5. In the Bohr or nuclear model of the atom, of course, we have a nucleus which contains protons, which are positively charged, and neutrons. In this model, the electron is positioned in the shells surrounding the nucleus. Protons are given or thought to have a mass of 1, as are neutrons. An electron has a mass around 1/2000th of the mass of a proton. It has a single negative charge. In each atom, the numbers of electrons is equal in number to the number of protons. So we'll move on to how the electrons are arranged in these shells. That is the electron configuration. So the number of protons in an atom is given by the atomic number. So on the periodic table provided by the Cambridge board, the atomic number is the upper number. So atomic number 4 for beryllium, atomic number 19 for potassium. Now that is relevant because that tells us the number of protons, which is equivalent in an atom to the number of electrons. So the atomic number is defined as the number of protons, but it is equivalent in an atom to the number of electrons. So if we take chlorine, it's got 17 electrons. Well, we can position 2 in the first shell, got a maximum of 2. The second shell has a maximum of 8. That leaves 7 to be placed in the third shell. Now in paper 2, electron configurations are usually presented in this format. 2, that's the first shell. 8, that's the second shell. 7, that's the third shell. If we look at beryllium, 4 electrons, so that's 2 in the first, 2 in the second. 2.2 is the electron configuration. Potassium got 19 electrons. So if you look at this diagram, you'll see that there are 2, 8, 8, and then the 19th electron is placed in the fourth shell. The position of an element in the periodic table tells us about the electron configuration. For example, if we think back to the last slide, beryllium, member of group 2, well, it had 2 electrons in its outer shell. That is true for all elements in group 2. All elements in group 2 have 2 electrons in the outer shell. We wrote the electron configuration for potassium that had 1 electron in its outer shell. Guess what? It's in group 1. And from the previous slide, chlorine was 2, 8, 7. It's in group 7. It has 7 electrons in its outer shell. So as a general rule, the group number is the same as the number of electrons in the outer shell of each element in that group. So all the elements in group 2 have 2 electrons in their outer shell, etc. But we can also make a conclusion from the period in which the element appears. For instance, beryllium in the second period, so this is period 1, period 2, the horizontal rows, has an electron configuration 2.2. Well, it's occupying or has electrons which occupy or are placed in two shells, the first and the second. So the second, everything in the second period, all the elements in the second period have electrons in the first and second shells. Chlorine was 287, well, it's in the third period. It has electrons placed in three shells, the first three shells. We say the three shells are occupied. And potassium, 2881, well, that's in the fourth period. Guess what? There are electrons placed in the first four shells. So the group number will tell you the number of electrons in the outer shell, and the period will tell you the number of shells that are occupied. To achieve the electron configuration of an ion, you're expected to combine a number of ideas. So I'm going to do a couple of examples and then leave you with a final problem, the oxide ion. So let's look at fluorine and the fluoride ion. So starting with fluorine, how many electrons has it got? Well, as an atom, it has 9, and its electron configuration therefore would be 2.7, as we saw on the previous slide. But if we go to the fluoride ion, it's 1-. That means it has an extra electron compared to the atom. So the atom has 9, but the fluoride ion has an additional electron, so it has 10 electrons. So its electron configuration must place 10 electrons in shells, 2 in the first and 8 in the second. So for a negative ion, the atom has gained an electron. Fluoride ions have 10 electrons, 1-, compared to the fluorine atom, 9. Now aluminium, if we look at the aluminium atom, 13 electrons. So we have 2.8.3 as the configuration for the atom. But the aluminium ion is 3 positive. So it's lost 3 electrons. Remember, electrons are negatively charged. So the aluminium ion, 3+, has lost 3 electrons. So it only has 10 electrons. We need to place those in shells, 2.8. So it has, typical exam question or solution to an exam question, it has the same electron configuration. Aluminium 3+ and fluoride 1- have the same electron configuration, but they have different charges, of course. You might like to stop the lesson and just write out the electron configuration for the oxide ion. Come back to check when you are ready. Okay, I'm going to reveal. Well, the oxide ion is 2-, so the atom has 8. The ion has gained 2 electrons, so the oxide ion again has 10 electrons, so 2.8. So I've chosen these 3 ions to illustrate the fact that 3 different ions can have the same electron configuration, as often questioned in paper 2. But a negative ion has gained electrons, a positive ion has lost electrons. And once you've decided on the number of the electrons, just write out the electron configuration, placing the electrons in shells in the normal way. So the usual advice, you need to practice some past paper 2 questions. You'll find this topic around question 4, question 5. If you haven't got access to past papers from your teacher, the Physics and Maths Tutor website, if you Google that, you will have ample access to a full record of CIE GCSE Chemistry papers. If you found this lesson helpful, please recommend it to a friend. Please like, and if it's not too much trouble, please subscribe. Thank you.